Afternoon. Today we're going to be looking at hyperbolic PDEs. So we previously looked at elliptic, which is the we looked at the Laplace equation, and that's what your lab sheet 3 is on. The second type of PDE we're going to look at is hyperbolic. This tends to be the most common type of PDEs which are used in modeling. Okay, so we're going to spend a couple of weeks on these before looking at parabolic PDEs, and then we'll come back to these when we look at systems of PDEs. Okay, so hyperbolic PDEs is what we're looking at today, page 43 in the lecture notes. So hyperbolic PDEs, what are they used for? Well, mainly used to model propagation problems. So any problem where you have a movement of a quantity across the domain. Okay, common examples, fluid flow, that's my particular research area. Weather forecasting, okay, so if you watch the news and you get your weather forecast, that's that when they forecast the weather, what they're doing is they're solving hyperbolic PDEs over a series of different things such as temperature, pressure, density, etc. Aerodynamics, that's a big one. So when you're designing cars or bicycles or aeroplanes, also use hyperbolic PDEs in aerodynamics. Blast wave analysis, okay. So anything which has a movement of something from across the domain, okay. So for example, with fluid flow, you could have a wave and the wave will travel across across the domain. The independent variables for hyperbolic PDEs are the spatial coordinates, x, y, and if you extend to the third dimension, z, okay, and also time. So this is where they differ from the elliptic PDEs. Elliptic PDEs didn't have time as an independent variable. You had steady state solutions. Hyperbolic PDEs do have time. So what this means is that solutions do not stay steady, okay? They don't stay constant. The solutions will change over time. With hyperbolic PDEs, the solution has to satisfy the PDE itself, the initial conditions, and the boundary conditions. So those are three things that solutions have to satisfy. With the elliptic, okay, it only had to satisfy the PDE and boundary conditions. So whatever the initial conditions were, it didn't matter because you had a steady state solution. But because hyperbolic PDEs also have this time independent variable, okay, solutions also have to satisfy the initial conditions. Okay, so if you change the initial conditions, you're going to change the whole solution. One feature of hyperbolic PDEs, which is not shared by the elliptic or parabolic, is the solutions can contain discontinuities. Okay, this is quite rare really in mathematics. A discontinuity is where you have an abrupt change in the solution profile. So for example, if you're modeling fluid flow and you have a wave and that wave's about to break, that may be represented as a discontinuity. So like an abrupt change in the profile of a solution. Okay, we're going to be looking at today and next week as well this equation here. Okay, so this is the advection equation. I'll mention more about it in the over the next few slides. But hyperbolic PDEs include quite a wide range of different different equations, mainly systems of equations, which we'll do in week 10. Okay, so in week 10, we'll be looking at what are called shallow water equations, which is a system of 2 PDEs. Austin uses hundreds of equations. Okay, you can do aerodynamics. Can use, for example, the Euler equations, which are a system of 5 PDEs. Okay, so we're going to start off with just a single hyperbolic PDE, which is this one. Okay, way back in the first week, I spoke about the range of influence and domain of dependence. Okay, essentially, the domain of dependence is a set of all points in the xt space that has some influence on a given point. Okay, so I'm just going to explain this graph, and then I'm going to give you a sort of more real world example. Okay, notice along the horizontal axis, I have an X domain. Okay, so I'm only going to assume a one-dimensional spatial domain. Okay, so here's my space domain. Okay, along the horizontal axis. This vertical axis is time. Okay, so as we go through time, the system and the solutions will change. Okay. Here I've got a point slap bang in the middle of my xt space. Okay, so this is some point in space and time. If this has some solution u at this point, for a hyperbolic equation, this point here is influenced or depends upon all these points in this region down here. Notice this region over here doesn't affect this point. Okay, so this point is only affected by a finite region. And likewise, if we were to go forward in time from this point has an effect on all of these points within this region up here. So that's the domain of dependence. So this point depends upon what's going on in the domain of dependence. And furthermore, this point has an influence on what's going on up here. Okay, that may be a bit difficult to follow. Remember, in the first week, I had an example. Think of a swimming pool. Right, swimming pool is absolutely flat. Okay, so there's no disturbance on the swimming pool at all. So it's been left for a while. Nobody's gone swimming in it, and it's absolutely flat. If you were to create a disturbance somewhere in that swimming pool, okay, only the area surrounding the disturbance would know about the disturbance straight away. Okay, so somewhere at the other side of the pool wouldn't know that there's been a disturbance. Okay, so as a disturbance, as the waves propagate, think of it like throwing a pebble in. So a pebble lands in the water and it causes circular waves of increasing radius. As those waves travel out across the surface, it gets bigger and bigger and bigger, and eventually a point over the other side of the pool will feel the disturbance. Okay, so that's what we mean by this. So let's say that's our disturbance. Okay, if I had a point up here, it's not going to feel that disturbance. Okay, but a point here will. Okay, so this is what we mean by range of influence and domain of dependence for a hyperbolic PDE. It doesn't affect all other points. Okay. And the boundary, okay, so I've listed these as x0 plus ct and x1 minus ct. These are what we call the boundaries, okay? These are the fastest and slowest moving waves, okay? So this point here, let's say there's a disturbance at this point, okay? I can draw these two lines stemming from that point, and that gives me the boundary of the range of influence. And these two lines will be the fastest and slowest moving waves from that point. Okay, so we'll be revisiting this later on when we start to talk about stability. Okay, so that's just one thing I want to do, just recap from that first week's lecture. Okay, so we're going to be looking in the next couple of weeks at this equation. It's the advection equation. It's the simplest PDE, and it's the simplest hyperbolic PDE as well. Okay, so this is the advection equation. So we have our u is the independent variable. That's what we're going to try and calculate. Okay, and the equation is the partial derivative of u with respect to time plus v times the partial derivative of u with respect to space. Okay, and that equals 0. Okay, u is the dependent variable, t is time, x is space, and v is the velocity of advection. Okay, so this advection equation is so called because it just models advection. Advection is just movement. Okay, it takes something from one location and moves it down a channel to another location. So, for example, if you had a river flowing past you and you were to dump some pollutant in the river, hopefully you wouldn't, but let's say you did, you can model that flow of pollutant down the river because it would follow the speed of the river. So let's say the river is flowing at 2 meters per second. You throw some pollutant into the river. After 10 seconds, that pollutant's moved 20 meters down the river. Okay. So it's actually a very simple PDE. It's actually a bit of a useless PDE in terms of modeling. Okay, so it's pretty useless, it doesn't do a lot. But what's useful about it is any scheme, any numerical scheme which we derive to solve this, if it doesn't work on this simple PDE, it's not going to work on more complicated examples. So we tend to use this as like a test. So we apply our schemes to this one, see if they work. If they don't work, we discard them, we're not going to use them. If they do work well against the advection equation, they may work well for other equations. That's why we're using it. It's kind of used as a test. For this PDE, if the initial conditions are given as a function of when t is 0 and for some value x, okay, so remember this u is a function of time and space. So when t is 0, that's our initial condition. If we know that, okay, the exact solution at time t is simply x plus velocity times time. Okay, it's just movement. Okay, speed is distance over time. Okay, so distance is speed times time. Okay, so you take your solution at time is 0, and all you do is you move it down by v times t, and that gives you the solution at time t. So it's dead easy to actually calculate the exact solution to this equation. Okay, right. So this is more of in a diagrammatic manner. Okay, what I've got here is I have a one-dimensional channel. As you can see, it's in the x direction, one-dimensional channel. This is my initial condition, so this is my function of u at time t equals 0. This is just made up by me, okay? It's just a sort of triangular profile. It doesn't matter what this is, okay? So if this is the initial profile, and what I've done is I've called this sort of bend in the profile x0, I've called this spike here x1, and this bend x2. Okay, what's going to happen after a period of time is it's going to be moved. That triangular profile is just going to be moved down the channel. Okay, notice in the blue graph at the bottom, I've still got exactly the same shape as the initial profile. It's just been moved down the channel. Okay, the distance that it's been moved is the velocity times time. Okay, so distance is speed times time. Okay, so this x0 point, which started here, that corresponds with this point on the domain at time t. Sorry, on the profile at time t, is just x0 plus v times t. So every point has just been shifted v times t down the channel. So that's what the advection equation models. So as you can see, it's kind of not a great model of anything really, okay, but we use it to test finite difference schemes and other numerical schemes against the advection equation, because if they don't perform well on the advection equation, they're not going to perform well on more complicated equations. Okay, so that's what the advection equation models. Okay, so over the course of this chapter, I'm going to look about half a dozen different schemes which we can use to solve this advection equation. There are countless schemes. However you want to approximate the finite derivatives and the derivatives in the advection equation will give you a different scheme. Some of them will work, some of them won't. Okay, I'm going to look at a few sort of common ones. So if you recall, this is what the advection equation is. Okay, similar to what we did with the elliptic equations, I'm just going to approximate the time derivative using a forward difference and the space derivative using a backwards difference. Okay, so remember the finite difference toolkit. Okay, that was chapter 2 in the notes. All I've done here is replace ut with a forward difference in time. Okay, so one step forward in time, so that we have the n+1 superscript, minus the current value, so it's the n superscript, all over the time step. Okay, dt is the step, the time step in time. Okay, so that's the forward difference, plus v, okay, the v velocity is there, multiplied by the spatial derivative. Okay, here I've used the backwards difference, so I've got ui minus 1, so that's the current node minus the node to the left. And that's divided by the spatial difference, delta x. Okay, so that's approximating those derivatives using those finite differences. What we can do with this one is rearrange to make this the subject. Okay, this superscript n+1 means this is a solution at the next time step. So what I can do is I can just rearrange this using simple algebra to get this as the subject equal and everything else on the right hand side. So let's do that. So first thing I'm going to do is subtract this second term from both sides. Okay, I've moved it over here. And then if I multiply both sides by delta t and then add this term, we get that. Okay, so that's simple algebraic rearrangement. What this means is the value of ui at the next time step is equal to some function of the values at the current time step. Okay, so all the superscripts here are n's. We know what they are. Okay, if you're starting off at initial conditions, the n's will be zeros, and you just have your initial conditions. Okay, so we know all of these values on the right hand side, and therefore we can calculate the next time step. Okay. What I did here is we approximated both derivatives using first order accurate finite differences. So what I say is, using big O notation at the end here, I say, okay, this is order delta t, delta x. Okay, so remember what that means is as these steps halve, we have a linear, or halve, as these steps delta t and delta x get smaller, we have a linear convergence to 0 for the errors. Okay, so that's what's called the first order upwind scheme. Well, actually, that's one part of it. Okay, the stencil. Okay, I showed you this last week. This is quite common to do. It just gives us a little bit of a diagrammatical representation of a scheme. Okay, this is my first order upwind scheme. Okay, the value of the ui at the next time step, okay, that is dependent upon the value at the previous time step and the node to its left. Okay, so this node here, okay, depends upon this node and this node. Okay, this is what we call a stencil. Okay, if the velocity, what we're solving for in the advection equation, if that's positive, what that means is flow moves from left to right. Okay, it moves starting from somewhere on the left, it moves down in a positive direction in the x channel, so it moves left to right. The area to the left of our node ui, okay, when v is positive, is known as the upwind direction. Okay, where is our wave coming from? Okay, so if I go back a couple of slides to here, okay, eventually, okay, this is our solution after time t. Okay, this is where our wave started, and this is where our wave ended up. Okay, anything to the left of this is upwind. Okay, it's what we call the upwind direction. Okay, but what if our velocity was negative? We'd have our wave or our profile traveling from right to left. Okay, so the upwind direction would be to the right. So if we look at this stencil here, okay, this node here, okay, if you've got a wave coming from the right, this node isn't going to know about it, okay, because this scheme only uses the node to the left. So our scheme does not use a node to the right, so we have a problem. We're not going to be able to capture that wave coming from the right. So to solve that, we simply take a forward difference to approximate the spatial derivative. Okay, so if I go back a couple of slides, okay, here we used a backwards difference, the UX. That gave us UI minus 1. So that's UI minus the node to the left. Okay. If you take a forward difference, we have the node to the right minus UI. Okay, so that's what we have to do if we have a negative value for the velocity. Same thing again, just rearrange using simple algebra. Okay, and here we get our, this is also a full first order upwind scheme, but this is when V is negative. Okay, and that has this stencil. So you can see if we had a wave coming in from this direction, okay, it reaches this node before it reaches that node. So this node can tell this node, hang on, they've got a wave coming in here. Okay. That's if you want to sort of like give these little nodes a personality. Yeah, you're all looking at me a bit odd there, but that's kind of what happens. Okay. Think of when I do this, I don't do this talk, but when I do talk in schools about mathematical modeling of waves, I get them to do a Mexican wave. Okay. I'm not going to get you to do it, you'll look too tired. But how do you know if you're in a Mexican wave? I take it you all know what a Mexican wave is. How do you know when to sort of stand up and cheer and go whoop? How do you know? Yeah, person next to you. Okay, how do they know? Person next to them. So think of hyperbolic PDEs like that. Okay, this node doesn't know when to change until this node does. And likewise, further on down. So if we had a wave coming in from this direction, this node would feel it. Oh, I say feel it, be affected by it before this node is. So that's why, if I go back a slide, if this one is when V is positive, so the wave comes in from this direction, and this one is when the V is negative. Okay. So the first order upwind scheme depends upon the value of V. Okay, so just to summarize, these are the same scheme. Okay, these are both known as the first order upwind scheme or FOU scheme. Okay, and they're different depending upon the sign of the velocity. Okay, it's first order in time and space, so it's not particularly accurate. Okay, we can improve on that, and that we'll try and do that later. The value of the next time step, which is the superscript n+1, is explicitly defined. Okay, it's quite easy to calculate the next time step because you already know the current values of u. Okay, this is important at the bottom. Application of these schemes to calculate the solution for the next time step is called a time marching scheme. Okay, so what we do is we start with initial conditions, and you march the solution forward by delta t each time. Okay, so we call this a time marching scheme. These are, unlike the elliptic equations, which required solution of the linear system using Jacobi, Gauss-Seidel, etc. These are explicit, so they're easy to solve. Okay, so what we're going to do now is we're going to test our first order upwind scheme. Okay, and we're going to test it against the advection of a Gaussian curve. So a curve that looks like the normal distribution, that type of thing. And we have to define a few things ourselves. Okay, here we'll be using a spatial domain in the range 0 to 1. So the smallest value of x is 0, and the largest value of x is 1. I'm going to use 101 nodes to discretize this. Okay, so I'm not going to do it by hand. Okay, I'm going to be using MATLAB in a minute. Okay, and this is my initial conditions. Okay, so this is the initial conditions when t is 0 and it's some function of x. Okay, and it's an exponential function with some quadratic polynomial. That's essentially a Gaussian curve. In this case, I've chosen to be minus 200 times x minus xc. xc is simply the center of the Gaussian curve. Okay, so this will give you a nice sort of bell-shaped Gaussian curve. Boundary conditions. Okay, I'm going to use transmissive. What this means is these are Neumann boundary conditions. There's 0 gradient across the boundary, which means the flow if I was allowed the wave to sort of flow out of the right-hand boundary, it would just flow out as if there were no boundary there. Hence, they're called transmissive. And the exact solution, okay, you notice this function down here is very, very similar to this function, except for instead of xc, we have xc plus vt. Okay, I know there's a minus there because obviously we're minusing it there. Okay, so that's the exact solution. We don't even have to do any complicated maths to find the exact solution of this advection equation. And we will calculate the solution over the range t. It starts at 0, and I'm going to calculate the solution up to a half. Okay, so just to, there's our initial conditions. Okay, so sort of hump, Gaussian hump. That's the initial conditions, and the exact solution after time t is going to be just the hump is moved to the right-hand side. Okay, so in the notes, I've given you a graph of, okay, this is what the solution to the first order Upwind scheme looks like. What I'm going to do now is step you through, take you step by step through doing that on the MATLAB. Okay, so hopefully the MATLAB is loaded up. Right. I'm going to call it advection. Okay, so what I'm going to do is I'm going to write a MATLAB code just to apply the first order Upwind scheme. Okay, and if you're probably used to me by now, first thing I do is clear all my workspaces. And I'm going to define variables. Okay, there are lots and lots of variables here, so I might forget a few, so let me know if I do forget any. Start with, I'm going to define the minimum and maximum values of my X domain. Okay, so minimum and maximum values of my X domain. I'm also going to define N. And N is one less than the number of nodes I'm using. Okay, so if I go back to the slide, okay, we said we're using 101 nodes. So the reason I said 101 is because one less is 100. Okay. What else do I want? I'm going to define a variable called t max. Okay, and that's the maximum value of t that I'm going to iterate up to. Okay, so I'm going to march the solution starting at 0. Oops, let's say t equals 0. Okay, I'm going to start at t equals 0 and go up to t max. Okay, so with that in mind, I'm also going to define a time step. I'm going to define this time step as being equal to 0.009. At the moment, this may be an odd choice. You may think, oh, that's a bit of a random number to use. It will become clear later on why I've chosen 0.009 at the moment. Okay, any other variables I need to define before I start? You're happy you know where these come from. These are just what we're selecting. Okay, so the first thing I'm going to do is discretize the domain. Discretize the domain. So what's my delta x going to be? Okay. So if I've got a x domain going from 0 to 1, and I've got n equals 100, what's my delta x? Yes, 1 over 100. So, or if I want to use x max and x min. Okay, so that's my step in the spatial direction. Okay, so then my x domain is x min, steps of dx to x max. Okay, what I'm going to do is just run that right now just to check that it's working. Okay, so it starts at 0, goes up to 1. Okay, so what I'm just about to do now is just go back to the slides, and I've just forgotten that, yeah, discretizing domain. Okay, Remember, we're using transmissive boundary conditions. This is just something I forgot when I was doing the MATLAB just now. We're using transmissive boundaries. Okay, that means Neumann boundary conditions means we need ghost nodes. Okay, because I want the gradient across this node to be 0. Okay, so that's the transmissive boundary. So therefore, I need values of a node to the left. So this is what we call a ghost node. We just make it up. It doesn't exist, so we just make it up. Okay, and in order for this node to be the gradient across this node to be equal to 0, the value of that node has got to be the same as the value of that node. And the same thing applies at the other boundary. Okay, so if we discretize the domain, okay, if n is 100, delta x is 1 over 100, and therefore this is our nodes. So our first node, okay, starts at minus delta x. Okay, so if this is x equals 0, this will be minus delta x. Okay, so where I just in the MATLAB code here, I should have actually gone from x min minus delta x all the way up to x max plus delta x. Okay, so if I run that, okay, you can see at my last value of x's includes a ghost node. Okay, so that's one thing we're going to have to add on. So I've added on 2 extra nodes at each end to act as my ghost nodes. Okay, I want to show you this slide here, which is also replicated in your notes. It's quite small because I had to sort of shrink it a bit to get it on the slide. This is the solution procedure, what we're going to do. Okay, so we start at the top. First thing we do, initialize variables. I think I've done that. I may have missed out a few, but I'll come back to it. Second thing we've got to do is calculate x and u0. That's what I'm going to do now. Okay, so u0 is my initial conditions. Okay, so calculate the initial conditions. Right, so I'm going to call it u0, and it's some function of x. I think this is off memory, so I might get this wrong. It's minus 200 times x minus xc to the power 2. Okay, I think that's right. What I haven't done is defined xc. So I'll do that here. And I'm going to have it centered at 0.25. Okay, these are my initial conditions. Let's check to see if I got those correct. Yeah, thank you. Okay, let's see if I got those right. So what I'm going to do is I'm just going to plot them against x. Ooh, looks like, oh no, there we go. So there's my initial conditions. Okay, it looks fairly okay. It's like what I'd expected. So notice whenever I'm adding something to my program, I'm checking whether it works. I'm not writing the whole program and then checking. I'm doing it sort of sequentially. Okay, so that looks fine. Okay, so what I'm going to do here is set my initial values of u equal to those initial conditions. And I'm also going to do un plus 1 as well. Okay, so that helps tidy things up later on. Okay. Right, so I've done that. If I go back to the solution procedure, okay. So for when I set n equals to 0, n is going to be my time step counter. Okay, set n equals to 0. Is n greater than n steps? N steps is simply the number of steps we require to actually march the solution. So our time step is 0.009. Okay, I want to get up to a half. Okay, so the n steps. Okay, n steps is simply the time you want to iterate to divided by the time step. Okay, so if I do that in the code, okay, so now I'm going to sort of march finite difference gene through time. Okay, so n steps is equal to t max divided by dt. Okay, what I'm going to do here is I'm also going to use the ceiling function. Okay, so that means it rounds it up to the nearest integer. So n steps would I think it's 56 or 55. Yeah. So in this case, n steps is something like 55.5 something. I round it up to the next integer just so I do a full step. Right. So I'm going to march the finite difference scheme through time. So I need a loop now, and this is my iteration loop. And the loop goes from for n equals 1 to n steps. Okay, so I'm going to perform n steps iterations of the first order upwind scheme. Okay, first thing I need to do, or if we go back to the flow chart, now I've lost the slide second one. If I go back to the flow chart, within the loop, I start by calculating the boundary conditions. You should do that before applying your finite difference scheme, because these boundary conditions are going to change the value of the boundary nodes. Okay, so in my case, the boundary conditions were transmissive boundary. So transmissive boundary conditions. Okay, the first node in U. Okay, that's our ghost node. Okay. When we do the mathematics and we use subscript notation, that's U minus 1. Okay. With MATLAB, we start our arrays at 1. Okay, so our first node here, that is our ghost node. Okay, that will be equal to the third node. Okay, that's node U1. So if I go back to this slide, wrong way, here. Okay, when we write it down in this manner, in this notation, that's a ghost node. It's got a subscript minus 1. In MATLAB, that's our node number 1. That's our node number 2, and that's our node number 3. So with transmissive boundaries, we want this value to be equal to that value. That's why, drop the mic, not in a cool sort of gangster rap style. But, yeah, so that's why we've got U1 equals U3. Okay, and we have to do that same to the other end. Now, I always get this bit wrong. I'm kind of adding 2 on for everything, aren't I? So I think an n plus 3. I might have got that wrong. It will tell me. It will tell me when I run it. It will be pretty obvious if I got that wrong. Okay, so hopefully I've got it right. The n plus 3 node. Okay, if n was 100, I've added 2 either side. Hopefully that's right. Anyway, so n plus 3 node is equal to the 2 nodes to the left of that. So it's just subtract 2 from whatever that is. Okay, so that's the boundary conditions. Next thing I'm going to do is calculate the first order upwind scheme. To do this, I've got to iterate through all my computational nodes. Okay, so I'm going to do an I loop for I equals 2 to n plus 1. I can't think there's n plus 3. I'll leave it there. I'll go n plus 2. Okay. 2 is my first computational node. Okay, n plus 2 should be my last computational node. Okay, and what I'm going to do now is just remind myself what the first order upwind scheme is. It's here. So I'm going to use this top one because I've got a v value which is positive. Okay, so all I'm going to do now is just translate this equation into MATLAB. Okay, one thing I did notice, I forgot to say what v was. And I'm going to use v as 1 in this code. Okay, so my un plus 1, the ith node is equal to ui minus v times dt over dx times the ith node minus the node to the left. That's my first order upwind scheme. Okay, so the next value of u is equal to some function of the previous value. Okay. Okay. But also, what I want to do is I want to create an animation of the solution going down the channel. So within the loop, I'm going to do a couple of plot routines. I'm going to say plot solution. I'm going to plot x against u. Oh, what I haven't done is update u. So u is un plus 1. Okay, so for the next iteration around, okay, u then becomes un plus 1. So for the next time I step through, I'm updating that solution. Okay, let's plot, let's use the circles and lines. And I'm going to pause it for a short period of time. Okay, let's see if that works. There we go. You see that? I'll increase the pause so it goes a bit slower. Okay. And what I can do is just make sure it's shown. Okay, so as you can see, it starts off on the left and propagates down the channel. Okay. What I want to do is how good is this solution? Okay. All right. Well, when I run this, okay, it goes down the channel. I don't know how good that is. It's quite difficult for me to see or compare it to the exact solution. So what I'm going to do in my code is I'm going to calculate the exact solution and also plot it alongside. Okay, so what I'm going to do here is calculate the exact solution. Right, so the exact solution, I'm just going to call exact, is equal to 200, oh no, exponential minus 200 times x minus xc minus b times t. Out 2. Okay, I think that's correct. I'm just going to double check with the slides. Where were we? How far back was it? Oh, not too far. There we go. Yeah, so that should be that function there. Okay, so that's my exact solution. So I'm going to just plot it. I'll plot the exact solution first. I'm going to use a red line to make it look cool. Hold on, because I want to plot another graph. Hold off. And I'm going to change my axes. Right. Oh, not moving. Ah, anybody tell me why it isn't moving? Okay, that's my exact solution. Anybody tell me why that isn't propagating down the channel? Sorry? Well, it's got T in there. Sorry? I haven't updated T. So T starts off at being 0 up here, but I never change it. T's never changed. So that was a mistake. So if I say T equals T plus dt, so then I'm adding the time step on T. Okay, there you go. So initially, the red line sort of was very close to the blue, but as you go down the channel, the blue line gets further and further away from the red. What I'm going to do is just run that again, but sort of expand. Okay. Okay, so as you can see, as we go down the channel, the blue, which is the computed solutions, aren't quite matching the red, which is the exact solution. What we have here is an example of dissipation. Okay, so we're losing some height. This is a common feature of first order methods. First order methods tend to smooth out the solution in the hyperbolic PDEs. What if I was allowing this scheme to go further? So I've stopped it at T max is 0.5. What if I go to 1? Okay. So as you can see, it goes down the channel, gets to the right-hand side, and hopefully I've done it correctly. It just passes through as if it wasn't there. Okay, that's using transmitted boundaries, and it's gone. It's gone from our domain. Okay, right. So that's essentially solving the advection equation. Okay, this is going to be the subject of the lab sheet 4, which we're going to do in a couple of weeks. Okay, so that was building the program. It's probably not perfect. I mean, you know, we could do some other stuff with it, but that's sort of the basic program. Okay, right. So I'm just going to run that one more time. Okay, so we've got this sort of dissipation happening. the blue line isn't going up as far. It should go up to 1, and it's sort of being smoothed out a bit. It's being dampened a bit. Dissipation is caused because we're only using a first order derivative, first order approximation for the spatial derivative. So the sort of obvious way which we can improve this, so that was the solution to the first order upwind. The obvious way which we can improve on this is use a higher order approximation for the spatial derivative. Okay, so what we're going to do now is, instead of using a first order derivative, I'm going to use a second order derivative in space. Okay, so there I've just sort of written out the advection equation again. Okay, this time, okay, I'm still using a forward difference for the time derivative, but now I've used a central difference for the space derivative. Remember, central difference was second order accurate. Okay, so doing very similar as I did before. Okay, rearranging, and I want this u superscript n+1 to be the subject. Okay, so this is quite similar to the first order upwind scheme, but we've got a denominator. We're multiplying the delta x by 2 here, and we're using nodes from both the left and right hand side. Okay, so this is known as forward time central space scheme, or FTCS. Let's have a look at the stencil for that. Okay, this is a stencil. This is a node we're calculating, and we require the UI node, UI +1, and UI -1. So we require all 3 nodes. Okay, we don't have to, as we did with the first order upwind scheme, we don't have to change our scheme depending on the value of V, because we have nodes to the left and right. So let's say you're in a football crowd, you got Mexican waves going around, you don't know which way they're coming from. If you've got a mate to your left and a mate to your right, you can take part if you want. Okay, I kind of like that analogy. Kids sort of get it straight away if I say that. And also I get them jumping up and down, and they like that as well. So would you like to jump up and down? No. Fair enough. Okay, that's the forward time centered space scheme. Okay, oh, spoiled it. What I could do is I can change my program, which I've just done, and I'm going to change it to the forward time centered space scheme. And to do so, we simply do that. Okay. See that I just changed. If I undo those changes, I started with that, which is first order upwind, and I made 2 changes, and that gives me forward time centered space scheme. Once you've got this, the basic code for this type of problem, you only need to change this 1 line. Okay, so this is using the forward time centered space scheme. Let's run this. Oh, things aren't looking good. Okay, hopefully you can see. Yeah, we've made a bit of a balls up there. Okay, what's happened there? Okay, what I'm going to do is actually take away the axis command so you can see what actually happens. Okay, can you see what's happening to the vertical axis is having to resize itself? Okay, as you can probably imagine, that's no good. Okay, something's happened there which caused our scheme not to approximate the actual solution. Okay, so I knew that was going to happen. Okay, the reason why I've included the forward time centered space scheme is to show you, but you can't just willy-nilly put in some approximates of derivatives, rearrange it and use it. Okay, there's some things we have to sort of take into account. And this leads us on to something called stability. Okay, so this is an example of an unstable scheme. Not all schemes will be stable. Okay, so this is the plot of the forward time centered space scheme, and I've stopped it after t equals 0.15 just to show you, if I run it on any further, as you saw, it will just blow up, and eventually it just crashes the computer. Okay, so what we're going to look at now is the idea of stability, and in sort of more formal language, convergence, consistency, and stability. Okay, we've already seen FTCS scheme is unsuitable for solving the advection equation. Okay, it became unstable. What we should have is any numerical approximation should improve as our steps in time and space get smaller. Okay, that's theoretically what should happen. Okay, that's the whole point of our order and the truncation of the Taylor series. Okay, if you have a scheme where when you reduce delta t and delta x and the approximation improves, it's called a convergent scheme. In other words, the error is converging to zero as your time steps and your spatial steps converge to zero. Okay, we need a convergent scheme. What we could do is we can test for it empirically. So we could derive our scheme. We can write a program to test for it. Does it work? If it doesn't, we know it's not convergent. If it does, we know it's convergent. That's okay, but it tends to be time consuming, especially if you've got quite a complicated PDE you're solving. And it may be misleading. Okay, you may have, your solutions may look like they're unstable, but that might be because you've got a bug in your code. It might not be because the scheme is not convergent. Okay, so what we tend to use is something called the lax equivalence theorem. And it's quite simply stated, well, I say simply, a scheme is convergent if it's consistent and stable. Okay, well, I say it simply, but okay, we've got two words here which I haven't defined yet. Okay, so we're going to have to look at these. Okay, so we need to show that a numerical scheme is what we call consistent and that it's stable. Okay, so that's called the lax equivalence theorem. So what's consistency? Okay, well, in your notes, I've got quite a sort of standard definition of consistency. In other words, it's consistent if the difference between the exact solution, remember we use big U for the exact solution, little u for approximation, if the exact solution minus our approximation tends to zero as delta t, delta x tends to zero. Okay, that's the definition of consistent. Okay, how do we show that? Okay, so if I was to give you a scheme and I haven't told you how I've derived it, okay, so therefore you don't know where it's come from, what finite differences I've used, we need a method to find out whether something is consistent. So to do that, what we do is you get your scheme and you replace the U terms with corresponding Taylor series. Okay, and you rearrange what you get so that you eventually end up with the PDE which you're trying to solve plus some other terms. Okay. If those other terms show that the truncation error tends to zero as our steps tends to zero, then you say, okay, I've got a consistent scheme. Okay, so what you're looking for is you get your scheme, replace it with Taylor series, rearrange it. What you're hoping to get is you're hoping to get your PDE plus some error terms. If you get any other terms, your scheme isn't consistent. Okay, and furthermore, we can say the formal accuracy of the scheme is determined by the truncation error. Okay, so what I'm trying to do now is I'm just going to go through this example. The example is actually given in your notes, but I thought it would benefit from me sort of showing you the working out. So I want to show that the forward time center space scheme is consistent. Okay, so I'm going to do this on the visualizer now. Right. As I say, you have got this in your notes, but sometimes it does help to see somebody go through it. Right. Oh, and I zoomed in a bit too far there. Where's the edge of my paper? Okay. Right, so what I'm going to do is I'm going to start off with the FTCS scheme. Okay, that's my scheme. Okay, wherever you see a U in that scheme, I want to replace it by a Taylor series. So I've got this U here, I've got this U, and I've got those two over the other side. So what I'm going to do now is I'm going to write out the Taylor series for those. Okay, so I've got un plus 1. Okay, so I'm going to write out what this Taylor series is. Now, the superscript n plus 1 means that's forward in time. That's t plus delta t. So I've got u plus delta t u, derivative with respect to t, and I'm going to stop it there. Okay, so I'm just going to write down the first order Taylor series. Okay, so remember the n plus 1 means, okay, that's a step forward in time. Okay, so our delta t is our h, and we find u with respect to t. Okay, what about u I plus 1? Okay, this means we're going forward in space, so plus delta x. So we have u plus delta x, ux, and that's a first order. So our higher order error terms are order delta x squared. Okay, and finally we got this one which goes backwards in space. So instead of u plus delta x, I've got u minus delta x, ux. Okay, I haven't bothered writing out the Taylor series expansion of that one because it's just u. Okay. So what I'm going to do now is I'm going to replace all the u's in that scheme by these Taylor series. Okay. So I've got this one here, which I'm going to replace by this Taylor series. Ut order t squared. Okay, that equals u. Okay, that u is just that one there. Or this u here is just the value of u. Okay, it doesn't need a Taylor series expansion. Okay, we only use a Taylor series where we're having a neighboring node. So this is a node to the right, that's a node to the left, and that's a node forward in time. Okay, this node just is written down as u. We've got minus v times dt over 2 delta x. Okay, I'm probably going to have to use two lines here. Okay, so first I've got this Taylor series, the ui plus 1. That's minus, okay, this one. Okay, so it's minus u minus delta x. Okay, because I'm subtracting this one, got a double negative here, so that's a positive. Oh, okay, okay. Remember, these order values, okay, they're not, all they are is they gives the behavior of the higher order terms as dt or dx tends to 0. They're not in itself values. They're just some hints of some form of behavior. Okay, what we want to do now, this is our forward time center space scheme with the Taylor series replacing all of those u's. I want to rearrange that to give the advection equation. Okay, so what I'm going to do is, well, if I subtract u from both sides, okay, I get rid of a u there and I get rid of that u. So I'm going to subtract u from both sides. Okay, can I simplify this? Well, I've got a u there and I've got a minus u there. So I'm going to just cancel those out. I've got delta x ux plus delta x ux. So that's 2 delta x ux. And I've got higher order error terms of second order. Okay. I don't add these together because adding their behavior doesn't do anything. So all I do is I say, okay, that those higher order error terms are just going to behave like that. Okay. So, okay, so I'm starting to simplify a bit more. I could cancel out the 2 delta x on the bottom. Okay, so if we do that, okay, so the 2 delta x cancels out with that. Okay, so I get minus v dt ux. Okay, and if I divide order delta x squared by delta x, that changes its behavior. Okay, so remember when we dealt with chapter 2, okay, order delta x squared divided by delta x gives me, yeah, so just give me order delta x. Yeah. Okay, all I've got to do now is something quite simple. Add this to both sides. Oh, actually, I'm going to divide by delta t. If I divide by delta t throughout, I get ut plus order dt, okay, equals minus v ux plus order delta x. Okay. Have I missed something out there? Yeah, I think that should have been, yeah, there should have been power there. Okay, now what I need to do is if I add v delta x, v ux to both sides, I get ut plus v ux plus order dt plus order dx squared. Okay, here you might recognize this as the advection equation. Yeah, sure. Should I have a what, these? Up here. But I've got one u there and then minus u there. Yes, that's. I could have had the other one negative, but these aren't really values; they're behaviors. Okay, these represent a behavior of the error as delta x tends to 0. Okay, they're not in themselves a value; they're valueless. They just say, okay, there's some behaviors going on here. Okay, so I know what you're saying, but what we tend to do is just ignore their. If I was to add this to that, its behavior wouldn't change. So I still say, okay, it's quadratic convergence. Tend to use big U's. Yeah. The little u convention tends to be sort of something we drop occasionally. When I start doing systems of equations, we use big U's everywhere. So I wouldn't get too hung up on whether they're big or little. Okay, so what we come down to is we're down to this thing. You may know this from previous slides. Yeah. What, here? That way. Oh. Yeah. Yeah. So when I divide throughout with this, what's happening here is if I had expanded these out to third order terms, okay, one would be plus and the other would be plus, and we'd have delta x cubed. Okay, that cancels out in this step. So if you pretend these two were expanded out to third order. Yes. So you're wondering where that's come from, are you?
is that one. You divide it with two different x.
Yeah.
And it should become minus v beta t and beta x. And the other one should be as well.
Yes, that should be divided by delta x as well. What?
But why you got one power two? Power one?
Yes, no. What we have is if this was expanded to third order, we'd have third order terms cancelling out. These would be x to the 3, delta x to the 3, delta x to the 3.
Oh, that's
Okay, so when you do it, you can cancel it out there. Try it. I mean, if we were to have plus delta x over 2 second derivative term plus squared. Okay, if we were to have used a further term, that would get cancelled out in here, and these would change to 3. Okay, so just pretend that's towards the end. Okay, so we'd have delta x cubed. Okay, so if we were to do that, these are all delta x cubed. When we divide by delta x, we get delta x squared. So essentially, these terms here, they cancel out. They just disappear. So yeah, so that's where.
Maybe that one is power two. Power three is bigger.
Yeah. So. Okay. These type of consistency questions can be a bit tricky. Okay. Well, especially when if you do the first order upwind scheme, which I may ask you to do in an exam, perhaps. Okay. It gets kind of fun. Okay. So eventually, you want down to the PDE you're trying to solve plus your error terms. Here, okay, we haven't got any other terms messing up our solution. So therefore, we can say the FTCS is consistent for the advection equation. Okay. FTCS is consistent for the advection equation. Furthermore, it's first order in space, first order in time, second order in space. We can say it's first order in time, second order in space. Okay, so when we talk about formal accuracy, this is what we mean. Okay, we take our scheme, we deconstruct it down to the original PDE plus our order terms. Okay, these order terms are the formal order accuracy. Sometimes you can get mixed. Okay, you can get you can start using first, second, fourth order for your spatial derivatives. Sometimes things get mixed. Okay, this is what gives us our formal accuracy. Okay, so it's consistent, but when we ran it, when we showed the solution, we showed that it was unstable. Just because a scheme is consistent doesn't mean it's stable. It has to be both consistent and stable to be convergent. Okay, we want a convergent scheme, we have to show it's consistent and stable. Are you okay with that there? I mean, do you want me to take it off? Or? I mean, it's at the top of page 50 in your notes, that bit.
Should be 3 after this one.
Sorry?
No, this one should be 3.
Yeah, I mean, it doesn't necessarily have to be 3. It's just when you're talking about order with the O delta X, they're behaviors. They're not like terms. So we're not.
When dividing with the X, that's what.
Yes. So yes, I mean, you've got to. It's kind of you are right. Yes, but these aren't values. They're behaviors. So.
No, in order to dividing with the X, should be open is being power of 3.
If you want to put them as 3, that would still be right. Yeah. If you want to write them as 3, that would still be okay. Okay, so that was that worked example, and that's given at the top of page 50. So the forward time centered space scheme is consistent, but it's rubbish. Okay, we've seen it's rubbish because going back a few slides, it doesn't give us a very good solution, and it goes unstable. Okay. So we've got to look at stability. So as well as being consistent, Lax's theorem says we've got to be stable as well. And what's the definition of stability? Well, essentially, if this is your exact solution, this is your approximated solution, and epsilon is some error. Okay. So as we march forward in time, we'll have a series of these errors. For each node, we'll have a series of errors. Okay, and if this sequence of errors, as we go to infinite number of steps in time, remains bounded, the scheme is stable. For some reason, there's some words missing there. Hopefully, yeah, they're okay on your notes for some reason. Oh yeah, sorry. Yeah, the scheme is considered stable if the sequence of errors remains bounded. Okay, so these errors can't grow. Okay, they're not going to be zero. They are going to be some errors because we're only approximating, but they can't be allowed to grow and amplify. Okay, that's the definition of stability. Okay, stability is determined by a couple of things. We're going to look at one of them today, and next week we're going to be looking at something totally different using Fourier series. But for today, the last thing we're going to be looking at is what's called the CFL condition. Okay, so this is to do with stability. The CFL condition, what you have, well, with time marching schemes, the larger your value of delta t, the less time steps you need to actually reach your end time. Okay, so if your delta t is larger, less time steps, less computational effort, everyone's a winner. Not quite as simple as that, because if you set your time step to be too large, your scheme will become unstable. Okay, well, an explicit scheme will become unstable. So there is a limit on how big we can have our delta t. And that limit is called the Courant-Friedrichs-Lewis condition, or CFL condition for short. Okay. I should warn you here, though, the CFL condition must be satisfied for a scheme to be stable. But just because it is satisfied doesn't mean the scheme is stable. Okay, so in other words, if you violate the CFL condition, your scheme is going to be unstable. Okay, no two ways about it, it's not going to work. But if you adhere to the CFL condition, that's no guarantee that your scheme is still stable. Okay, so this is our first sort of protocol for when we're looking at stability. Okay, we want, for computational reasons, we want delta t to be as large as we can have it. Okay, but we still need to make sure this condition is satisfied. Okay, and one of the first slides I showed you today was about the range of influence and domain of dependence. Okay, so we're going to use that in a minute. But before I do that, I want to introduce the idea of the characteristic curve. Okay, what I've done here is I've got the exact solution to the Gaussian curve propagation problem. Okay, so along the bottom, I've got my x domain. Along this way, this is my t domain. Okay, so all I've done is I've calculated it once here, moved t forward a bit, calculated it again, moved t forward a bit, calculated again, and I've created a surface plot. So this is like a plot as it moves through time. So it starts off here, and as it propagates down the channel, I've plotted it in what we call xt space. Okay, so that's my Gaussian curve through time. Okay, what I'm going to do now is overlay what we call a characteristic curve. Okay, you can pick any point on the curve, and we can trace through time the equivalent point as it moves. So, for example, if I was to take a point, say there, which is on the front face of the curve, the equivalent point up here would be about there. Okay, equivalent point up here would be about there, something like on the first front of the curve. So what I'm going to do is I'm going to take the peak. Okay, so our peak of our curve started at there, which is 0.25. Okay, when time is about 0.3, our peak is about there. Okay, and what I'm going to do is I'm going to join those points up. And by doing so, that's what we call a characteristic curve. Okay, it shows you through time and space what's happening to that point. Okay, so that point starts here, and eventually, after half a second, it ends up over here. Okay, and that blue line is what we call a characteristic curve. And that curve, well, in this case, it's just a straight line because we have, this is a linear problem. It's a linear PDE. That curve has the linear equation x naught, which actually should be down here, plus the velocity of our propagation times time. Okay, so that's our characteristic curve. With that in mind, I'm going to revisit the idea of domain of dependence. Okay, and the CFL condition states that the physical domain of dependence must be contained within the numerical domain of dependence. Okay, what are physical and numerical domain of dependence? Well, I've defined them here. So the physical domain of dependence is essentially all of those points in the physical space that has an influence on our point. So if you take a point, let's say UTX, it's all of the points that have an effect on UTX. Okay, so it's a domain of dependence, but this is a physical domain. Okay, this is what comes about through the PDE. Okay. We've got a numerical domain of dependence. Now this is defined by the region that contains all of those nodes that has an effect on the value of the approximation of UTX. Okay, so the physical domain of dependence contains, it's a region. Okay, it's a region in space, space-time, so TX. Our numerical domain of dependence is a set of nodes. Okay. What we're saying for the CFL condition is a physical domain of dependence must be contained within the numerical domain of dependence. Now, that may sound a bit tricky. It's a lot easier when you start to look at some diagrams. Okay, so this is first diagram. This is when we got CFL conditions satisfied. So what we got up here is this is our any point within our domain at some time. Okay, the physical domain of dependence is represented by this region here. So this is a set of all points that may have an effect on the value of that point. Okay, that's a physical domain of dependence. The numerical domain of dependence is defined by the set of these nodes. Okay, all of these nodes which are colored in black here, which have an effect on our approximation at that point. Okay, so in this case, let's say this is a forward time center space scheme. That node depends upon the previous node and its left and right neighbors. Okay, each of these nodes on this level depend upon their previous node and their left and right neighbors. Okay, so in this case, the numerical domain of dependence is given by this, well, the boundary is given by this dashed line, and all these points are colored in black. The physical domain of dependence is given by that gray area. Okay, that's when it's satisfied. Okay, we have the CFL condition satisfied. It's contained, the physical domain is contained within the numerical domain. When it's not satisfied is when this occurs. Okay, so again, we've got this very similar diagram. Here, we got points which exist outside of the numerical domain, which should have an effect on that point. But because they're outside, they can't be captured by our scheme. Okay. Usually this happens when we've got very fast moving waves. Okay, so these are characteristic lines. So if I go back about 4 slides, that characteristic line, this blue line, lines of those types are these boundary of the physical domain. Okay, this is when it's not satisfied. Okay. Anybody sort of give a sort of guess on how we could make it so this would be satisfied? How can I make this physical domain, this sort of gray region, how can I make this fit inside this region? Sorry? Yes, could do. Yeah, so instead of just using for this one, I could use that node there and that node there. That would work, yeah. Another way we could do it is we could increase our delta x. If I was to stretch out my nodes, if I was to increase, let's say, the gap between these two nodes until like this node comes over here, that would work. Or I could decrease delta t. I could sort of squash it. Okay, so I could stretch out my nodes in the x direction, or I could decrease delta t. What we tend to do is when we discretize a spatial domain, we tend to keep that constant. We don't mess with our gaps of our delta x. What we can do is we can change our delta t. We can reduce it. If we reduce delta t, this sort of domain, this physical domain, can be moved inside our numerical domain. Okay. Right, so how would we do that? Well, if we look at the advection equation, velocity is constant. Okay, so it's set at the beginning and it never changes. So what we have is v times dt. That is the distance that our characteristic has moved over one time step. Okay, velocity times time. So our characteristic moves that distance over one time step. We've got to make sure that that distance is less than our delta x. Okay, so if I go back to the one where it's satisfied, this is what we've got to ensure. But let's say from there to there, okay, that distance, that horizontal distance, has got to be less than our delta x. We can rearrange this. Okay, if we divide both sides by delta x, we get this. If we divide both sides by delta x, we get 1 on that side. So we've got to make sure that this number, remember delta t, delta x, just numbers, so is velocity. This number has got to be less than 1. We call this number the courant number. Okay, we often use c, or nu is often another number used. Greek character nu is often another number used there. So c is our courant number. Okay, that c will be different for every numerical scheme. Okay, there will be a value of c for a numerical scheme which will mean it's stable. Most of them have a value of 1. Some of them don't. Okay, so it depends upon what scheme you're using. C is set to some value that ensures the scheme is stable. We'll look at that next week. Okay, if delta x is constant, we usually have it as constant, then our time step is given just by a simple rearrangement of this formula up here. Okay, c is a number. We set that. We set that so it's stable. Multiplied by your spatial step, divided by the velocity, that gives you what we call the maximum allowable time step. Okay, so your time step is limited by c. Okay, that's what we mean by the CFL condition. Okay, we have to make sure this condition is satisfied. What I'm going to do quickly is go back to my code. Okay, and at the very beginning of the code, I set dt to be 0.009. Okay, and I mentioned, hang on, that's quite an odd number. Why did I use 0.009? Well, I'm just going to undo the. So I'm back to the first order upwind. Yeah, the reason being is this c value for which the first order upwind scheme is stable is 1. So c has got to be less than 1. So what I did is I set c to be 0.9. So if c is 0.9, that ensures it's less than 1. My delta x was 1 in 100, and v was 1. So 0.9 times 1 in 100, 0.009. Okay, that's why I set it. So, but when I run it, it's stable. Okay, first order upwind scheme, it's stable. What if I was to use a different value of delta x? Delta t. Let's say I multiply it by 10. Run it again. Whoa! Straight away, it's gone unstable. Okay. What if I only just go over it? Okay. So what if I just do 0.11? Okay. So 0.01 should give me stability, but what we have is with computers, a value in a computer is not exact. It's exact as 16 decimal places, but you might be just over. You might have, if I was to put 0.01, okay, I am specifying this as 0.01. The computer, deep in the bowels of it, might say this is 0.01. Okay, that little 1 way down will cause this to be unstable. So we never go to the limit of stability. Okay, if I just go slightly over, okay, it's starting to overshoot. Okay, if I was oh, you can see some oscillations coming in down here as well. So just going 0.01 over means it's unstable. Okay, so that's why I had that at 0.009 to make sure I had a stable scheme. Okay, how do I know that C was equal to 1 for this scheme? Well, that's to do with what we call von Neumann stability analysis, and that's what we're going to do next week. Okay, quite a lot of theory in that lecture. If there's anything to take away from it, it's the way we solve things is by keep approximating derivatives using finite differences, rearrange them, and we get a time marching scheme. Are there any questions? Sorry? Good question. So if I say if delta x equals delta t, well, that would mean that my n would be x max minus x min over dt. Oh, didn't like something there. Let's round that to the nearest integer. Oh, didn't like something there. Don't know. Yeah, I'd have to look into that. But what if, you mean this one?
Yeah.
If that was the case, V, it would be unstable because V, unless V 0, it's not less than 1. Oh, sorry, no, if V would have to be less than 1 for it to be stable. Because delta t over delta x will be 1. Multiplied by V has to be a number less than 1. So V would have to be less than 1. Yeah, can do. Yeah, so we've got to set delta t to be stable. Sorry? Yes.
But in the nature, in motion, there are no velocity less than 1.
You can. You can have a very slow velocity. You can have velocity less than 1. Yeah. Well, this is unitless here. If I walk at 1 meter per second, what if I walk at ½ meter per second? That's velocity less than 1.